Hello everyone, welcome to week 6 of the lecture series. So today we will discuss the questions. So welcome to the week 6 of this lecture series tutorial session. You are not audible. Right. Huh. Can you, hello. So welcome to the week 6 of this lecture series. So today we will discuss about the questions based on the lecture taught in the week 6 of the at the NPTEL portal. So basically today we'll cover one question on jet transform, and after that we will go on to the Fourier series, and we will mostly discuss about the Fourier series in this tutorial session. So before moving on, uh, let's solve a question on jet transform first. So this question is based on the difference equation. So solve the difference equation yn plus 3y of n minus 1 equal to xn, and here the initial condition given are with the y of minus 1 equal to 1, and determine yn for the input xn equal to 8 un. So our input is given as xn is equal to 8 un, and in this question it is given that yn plus 3y of n minus 1 equal to 8 of un, because we have substituted this value of xn in the given difference equation. So now we'll do z transform. We'll get yz plus 3z inverse of yz equal to 8 by 1 minus z inverse. We know that this z transform of un is 1 by 1 minus z inverse. That is also equal to z by z minus 1. So after that, we'll take yz term common, and we'll get as so here. Actually, this question is based on the unilateral transform, because also the initial conditions are given, that is y of minus 1 is equal to 1. So in this case, this difference equation will not be same as the previous case for unilateral transform, as we have discussed in the Laplace transform also. So in that case, here it will be y of z plus
Sir, no audio, sir.
Audio is not coming. Oh, no. And now is it coming? Oh, sorry, I was like muted. So we were discussing this question. So the question is given as the difference equation is given and also the initial condition that is given, that is y of minus 1 is equal to 1. And after that we have to determine yn for the input of xn is equal to 8un. So similar to Laplace transform here for unilateral transform, like the properties is if if the z transform of xn is given as xz, then z transform of x of n minus 1 for the unilateral z transform, that is given as z inverse of xz plus x of minus 1. The same we will apply here, that is equal to 3 of z inverse of yz plus y of minus 1. So that is equal to 8 of un. So after that we'll take yz as common. Then we will get 1 plus 3z inverse plus 3, that is equal to, and the z transform of un is 8 into this 1 by 1 minus z inverse. So after that we'll get yz is equal to 8 by 1 minus z inverse into 1 plus 3 of z inverse, and this plus 3 will come this side, and this term will come in denominator, so it will be 1 plus 3 of z inverse, because we have divided the whole equation by 1 plus 3 into z inverse. So this we got. Now we will use the partial fraction expansion and residue method to calculate this. So here yz is equal to a by 1 minus z inverse plus take another constant b, that is 1 plus 3 of z inverse, and here it will be minus 3 by 1 plus 3 of z inverse. So we know that a is equal to 1 minus z inverse into this whole term, that is 8 by 1 minus z inverse 1 plus 3 of z inverse, and here we will keep z inverse is equal to 1, because we are calculating for this one. So z inverse we will keep as 1. So after substituting this value, this will first cut down. And a is equal to, we will get 8 by 1 plus 3, that is equal to 2. Similarly for b we will calculate. So for b it will be 1 plus 3 z inverse into 8 by this term. And here we will keep z inverse is equal to minus 1 by 3, because if you equate this equal to 0, we will get minus 1 by 3. So this term will get cancelled. So b is equal to 8 by 1 minus 1 by 3, that is 1 by plus 1 by 3. So it will be 4 by 3. So 24 by 8, 4, 24 by 4, that is equal to 6. So our yz becomes now 2 by 1 minus z inverse plus 6 by 1 plus 3 of z inverse minus 3 by 1 plus 3 of z inverse. So this two will get add, and we will get plus 3 by 1 plus z inverse. So now we know that yn, if we will take the inverse, this will become like, this is simply 2 by 1 minus 1 by z, that is equal to 2z by z minus 1. So this is 2 of un because the inverse of z by z minus 1 is un. Okay, and the next one will be like plus 3 into, and here it will be minus 3. So minus 3 of n into un. As you can calculate here, like 3 by 1 plus z inverse will be 3 by z plus 1 into z. So here it is 3z. Here it is 1 plus 3z inverse. So it will be 3 by 1 plus 3 by z, that is equal to z plus 3, 3z by z plus 3. So z plus 3 we can add z of minus 3. So here a is minus 3, so minus 3 to the power n un. So the final answer is yn is equal to 2un plus 3 into minus 3 to the power n un. So in this way we can find the yn by using the inverse Z transform. So now we will discuss about the Fourier series in today's lecture. There are different ways to represent a signal, like using sinusoidal way and also the complex exponential way. We will see each of them and we'll see how the coefficient is calculated. So we'll see first different. There are three form of Fourier series in the Gates levels. The first one is like trigonometric Fourier series, which is defined by cosine and sine signals. Second one is the exponential Fourier series, and the third one is the polar form. So we'll see basic of each three, and after that we'll solve many questions based on this. So basically, in Fourier series is like it is approximation of any general signal that is expressed as a sum of sinusoids, and this is done so that to represent the frequency domain of any signal. So we will first start with trigonometric Fourier series. So a periodic signal ft can be expressed as infinite sum of sine or cosine function in the trigonometric Fourier series. So here it is represented as xt is represented as a naught plus summation over n is equal to 1 to infinite an cos of n omega naught t plus summation of n is equal to 1 to infinite bn sine of n omega naught t. Here omega naught is the fundamental frequency, that is also 2 pi by t. Now we will like see how to find a naught, an, and bn, that is the coefficient in this. So basically, a naught is also called as the DC coefficient because it is independent of the frequency components. So for finding a naught, we'll integrate in the both the sides. So after integrating 0 to t xt dt is equal to, and when you integrate first I can write both the cosine and sine term together, because in both is depending on the variable n. So it is like this. So we will separate out a naught dt, and this term we will see, like if we exchange the integration and summation, then over a time period, the integration of cosine and sine signal, we know that that is 0. So this will lead to 0, and also this integration will also lead to 0. So our and this a naught is integrated, a naught is constant, so it will come out, so it will be a naught into t. So our a naught will be 1 by t integration of xt over the time 0 to t dt. So in this way, the a naught, that is a dc component, also it is known as this coefficient a naught is also known as dc component of signal. Similarly, if you if you do some simplification, you will get an is equal to 2 by t 0 of t x of t cos and omega naught t dt, and bn is equal to 2 by t 0 to t xt sine of and omega naught t dt. So this you can easily find, like in this just integrate both the side and multiply with cosine to find the an. So after that you will get the an, because the another integration cos and m omega naught t into sine n omega naught t will lead to 0. And for finding bn, just integrate both the side and multiply with sine n omega naught t. So in this way we can get an and bn. So these coefficients formula are very important. Now the next form is the exponential Fourier series. So in this, any signal xt is given as integration over n is equal to minus infinite to infinite cn e to the power j of n omega naught t, and here cn is equal to 1 by t integration over 0 to t xt e to the power minus j n omega naught t dt. And in the lecture also, it is proved that Cn is equal to, in the NPTEL lectures, An minus JBn by 2, and C of minus n is equal to An plus JBn by 2. So after that, we'll solve some question based on this. But before that, we can see the polar form of trigonometric Fourier series. So in this, xt is represented as d naught plus summation of n is equal to 1 to infinite dn cos of n omega naught t plus theta n. And this constant d naught is given as a naught and dn is equal to under root of an square plus bn square, and theta n is equal to tan inverse of minus bn by an. So these things are important. Now we'll solve some of the question. Before that, we'll see from here that we will see the magnitude spectrum and phase spectrum, like what are the properties of these. So here Cn is given as An minus jbn and C of minus n is An plus jbn by 2. So in this case, the magnitude of Cn will be, Cn is given as this. So the magnitude of Cn, that is equal to under root of An square plus Bn square divided by 2. That is also is equal to C of minus n. So magnitude of C of minus n. So the phase, like the magnitude spectrum is of even properties, like it is of even symmetric. So it will be like this. At omega naught, if suppose this is there, at minus omega naught, it will be equal. So because it is the even symmetry, like that. And if we see the phase, so angle of Cn, that is equal to tan inverse of Bn by An, that is equal to if you see the angle of C minus N, this will be tan inverse of minus Bn by An here, and angle of C of minus N, that is equal to tan inverse of Bn by An. So the phase spectrum is the of odd symmetric. So it will be of odd symmetric, like at omega naught, if some minus theta 1, then at minus omega naught, it will be some plus theta 1. So like this, it will be the odd symmetry. And also, we can see now, what happens if our signal xt is even, or if it is odd, then what is the value of this coefficient? So a naught, an, and bn. So let's take the next example. Like if xt is equal to x of minus t, that is, if xt is the even symmetric signal, then find a naught, an, and b naught. So here we know that a naught is equal to integration of, it is of even symmetric. So that's why, if let's suppose this integration is from minus t by 2 to t by 2 one time period, then we can write it as uh, 2 by t, because it is xt is equal to x of minus t, 0 to t by 2 xt into dt. And our an, that is also equal to, instead of 2 by t, it will be by 4 by t, and the integration will be 0 to t by 2 xt of cos n omega naught t dt. And bn will be 0, because the integration of sinusoidal signal, here minus t by 2 to t by 2, this term will lead to 0. and Bn is equal to 0. And similarly, if xt is equal to minus of x minus t, so the above case was for when xt is even symmetry. Now when xt is odd symmetry, then our a naught, that will be like 1 by t minus t by 2 to t by 2 xt dt. So this is the odd signal xt. So this integration will leads to 0. So it will be 0. And an, that is equal to 1 by 2 by t minus t by 2 to t by 2 xt of cos and omega naught t dt. And we know that xt is odd. So odd into odd signal will be odd. So here this an, this integration will also lead to 0, and only we will get bn term. So bn, that is equal to 4 by t from 0 to t by 2 xt into sine of and omega naught t dt. So in this way, like the coefficients will reduce if signal is even symmetry, then our bn will be 0. If signal is odd symmetry, then a naught and an will equal to 0. Now before moving to the further question, we will see uh, Dirichlet conditions for Fourier series. So like if a signal ft satisfies certain conditions, so its Fourier series is guaranteed to converge pointwise at all points where xt is continuous. So these conditions are known as the Dirichlet condition. So it should satisfy this condition. These conditions are sufficient conditions. Like the first one is that the integration should be like it should be absolutely integrable. So the integration of this value should be finite. So these, if these three conditions like is required for for guaranteeing that Fourier series is converging. The second condition is that it should have finite number of finite size discontinuities in one period. So in one period, finite number of discontinuity of finite value. So it is continuous, it should have some finite value, not the infinite. And third, it should have finite number of maxima and minima in one period. So now we'll solve some question. So this was the theoretical part of this week lecture. So we'll take some examples. Like a signal xt has time period of 1 unit and the Fourier coefficient is given as Cn is equal to minus 1 by 3 to the power n when the value of n is greater than or equal to 0, and it is 0 for n is less than 0. So we have to find the expression for xt. So we know that using the Fourier series, that xt is represented as summation over n is equal to minus infinite to plus infinite Cn into e to the power of j n omega naught t. So here Cn is given as minus 1 by 3 to the power of n dot e to the power j n, and we can write this omega naught as 2 pi by t into t. So after that, minus 1 by 3 to the power of n into e to the power of j n 2 pi, n is equal to 0 to infinite, because for n less than 0, the in summation like the Cn is equal to 0. So the summation will be from 0 to infinite only. N is equal to 0 to infinite. So minus 1 by 3 into e to the power of j 2 pi t, and here we'll take whole n as common, and after that, so this is the summation. So this will be equal to a by 1 minus of 1 by 1 minus of r. So this r will be minus 1 by 3 e to the power j 2 pi t. So we'll get 1 by 1 plus 1 by 3 into e to the power of j 2 by t. So in this way we can get our signal xt as this. So we'll solve a few more questions for finding the Fourier series. So let's take another signal. So find the Fourier series of this signal. So here we can see that time period can be written as 2 pi by omega naught, and Cn, that is equal to, we know that is 1 by t of 0 to t del t dot e to the power of minus j n omega naught t dt. So that will be equal to 1 by t, and this del t will be 1 at only t is equal to 0. So for other value of t, this we have to only integrate at small t equal to 0. So 0 t del t at here t is equal to 0. So this will be 1. So it will be 1 by t into t. That is, sorry, integration of del t is equal to 1. So it will be 1 by t. Because this integration will be 1. So our Cn is 1 by T, and we know that A naught is equal to C naught. That is equal to, because Cn is 1 by T, so here A naught will be C naught, that is also equal to 1 by T, and Cn is equal to An minus JBn by 2, and this is like even symmetric signal. So in this, our Bn is equal to 0. As you can see, this is even symmetric signal. So for even symmetric signal, Bn is equal to 0. So our Cn will be An by 2, and Cn is 1 by T. So An is equal to 2 by T. So finally, we can write our signal xt as A naught, that is like A naught plus An of cos and omega naught T. Here n is equal to 1 to infinite. And the Bn term, like this term, is 0. So our xt will be finally A naught, that is equal to, we have calculated 1 by T plus 2 by T summation over n is equal to 1 to infinite cos of n omega naught T. So this is our signal xt. We'll solve some more question. Before that, we can see some of the properties. First I will write directly the property. No need to see the proof for this, and we'll solve some question. Like let's suppose Fourier series coefficient of signal xt is Cn. Like we can denote in this way. Fourier series coefficient of xn is Cn. Then in that case, uh, like this also obeys the linearity property. Like if the Fourier series coefficient of xt is Cn, and Fourier series coefficient of yt is, let's suppose, Bn, then the Fourier series coefficient of this term alpha xt plus beta yt will be alpha Cn plus beta Bn. And next we will see time shifting property. In this, if the Fourier series coefficient of xt is Cn, then for xt minus t naught, the Fourier series coefficient will be e to the power minus j n omega naught t naught. Like whatever is the delay here, that is t naught. So we'll do e of minus j n omega naught t naught into Cn. The third one is frequency shifting. In this, if for xt it is Cn, then for e to the power of j m omega naught t xt, it will be c of n minus m. Also, we can like proof for this. like Fourier series coefficient of Fourier series coefficient is given as of, let's suppose the signal is e j m omega naught t into xt. So that will be 1 by t integration over 0 to t e of j m omega naught xt into the signal into e to the power of minus j n omega naught t. So when you do this, you will get 1 by t 0 to 2. Here we will take xt separately and e to the power of minus j n minus m omega naught t. So here if it is like we know that for xt Fourier series coefficient of xt that is equal to 1 by t. So this is cn is equal to xt e to the minus j n omega naught t dt. Here it is n minus m. So this term will be c of n minus m. And after that we will see time scaling and time shifting property, and we'll solve some question. So the next is this is third one. Fourth one is time scaling. So in this, if Fourier series coefficient of xt is cn, then for xat, the Fourier series coefficient will be cn only, because here the period is equal to t and here period is equal to t by a. The period will also change when we will like scale the signal. Because in the integration it will change. Like we can do the proof also. Like the Fourier series coefficient of x of at can be given as 1 by t by a 0 to t by a x at e to the power of minus j n omega naught at dt. So after that, let's here assume this at as tau. Then we will get this integration 1 by if at is tau, then a of dt is equal to d tau. So dt is equal to d tau by a. So we'll substitute dt is equal to d tau by a. And also this limits we will substitute like when t is tends to 0, then tau also tends to 0. Like if t is equal to 0, then tau is also a into 0, that is 0. If t is t by capital T by a, is imply that tau is equal to t into a, so it will be t by a into a, that is equal to t. So this will become now 1 by t from 0 to uh, t x of tau e of minus j n omega naught tau d tau, because here d tau like dt is equal to d tau by a. So d tau by a will come here, but here also t by a is there, so this a and a will get cancelled. And this we know that this is equal to Cn. So the it will in time scaling it will be Cn only. The last one is time reversal. Like a Fourier series coefficient of xt is Cn. Then for x of minus t will be C of minus n. So this we can easily prove. But now we'll take some example. the Fourier series expansion of a real periodic signal with fundamental frequency f naught is given by ZPT is equal to summation over n is equal to minus infinite to infinite Cn e to the power of j 2 pi and f naught t. It is given that C3 is equal to 3 plus J5, then find C of minus 3. So, like the signal is real periodic signal. So, we know that for real periodic signal, uh, as this is taught in the lecture in NPTEL, C of minus K is equal to CK conjugate. So, here C3 is given as 3 plus J5. So, we have to find C of minus 3, that is equal to Ck of conjugate. So that is the conjugate of 3 plus J5. So that is equal to 3 minus J5. So these are simple questions. If we remember all the properties and other things, it will be very easy to solve such questions. So next we will see the Parseval's theorem, as it is really important for the GATE examination. So this is also called as Parseval's power theorem. Let me check whether the video is recording or not. So this recorded lecture will be uploaded on YouTube and link will be shared in NPTEL portal. So if anyone missed it, can see it later also. So for a signal of if the Fourier series coefficient of xt is given as Cn, then Parseval's theorem says that 1 by t of 0 to t mod xt squared dt, that is equal to summation of n is equal to minus infinite to plus infinite Cn square. And this we know that this is also known as the power of signal. That's why it is known as Parseval's power theorem. So we can see the proof of this also. So we'll see the proof of this because this is important. So here in proof, first we'll write xt as summation over n is equal to minus infinite to infinite Cn e to the power of j and omega naught t. So we know that x conjugate of t will be n is equal to minus infinite to infinite Cn conjugate e to the power, here it will change minus j and omega naught t because it is conjugate of xt. So now we will find this integral which is on the left hand side. So 1 by t summation over 0 to t xt squared dt. So this can be written as xt into x conjugate of t dt. Okay. After that, we can write this as, and this x conjugate of t, from here we will write that is equal to summation of Cn conjugate e to the power of minus j and omega naught t. And this for this integration dt will be there. This can be further written as We will exchange this integration and summation. So we will get 1 by t 0 to t, and we know that like here what we have done 1 by t xt into cn conjugate of e to the power of minus j n omega naught t dt. So after that we have written this. So this will become summation of cn conjugate into cn. So that will be the cn magnitude of cn squared from n is equal to minus infinite to plus infinite. So this is also known as power theorem, Parseval's power theorem. Like 1 by t, I will write the final equation here. That is equal to summation over cn squared and this is equal to power of signal xt and also known as Parseval's power theorem. So we will see some questions. So we'll take one example, that is find the power of the signal xt up to second harmonic. So up to second harmonic means we will take the coefficient up to c of 2 and c of minus 2 only. So the signal is given here xt 0 to 1, 1. So the fundamental period is equal to 2 here. As you can see, for every 2 unit, the signal is repeating. So omega naught is equal to 2 pi by t. So that is equal to pi. So here we can define our signal xt in fundamental period. In fundamental period, xt can be defined as 1 when t is between 0 to 1 and 0 when t is from 1 to 2. And we know that coefficient Cn can be found as 1 by t 0 to t xt into e to the power minus j and omega naught t dt. So here in this case we can write half from 0 to 1 it will become, because time period is t is equal to 2, so we'll write 1 by 2. From 0 to 1 it is e to the power minus j and pi t, and plus from 1 to 2 it will be 0 dot dt. And after that, Cn is equal to the integration of the this term will 0, and for this term it will be e to the power minus j n pi t by minus j n pi. It is from 0 to 1. So we'll get half 1 minus e to the power of minus j n pi divided by j n pi. So what we can do, we can we can do some simplification. We'll take e to the power of minus j n pi by 2 common. Then we'll get e to the power of j n pi by 2 minus e to the power of minus j n pi by 2. And here it will be 2 of j n pi. So this we can write as e to the power of minus j n pi by 2 divided by n pi, and this term, like this term will become e to the power of jn pi by 2 minus e to the power minus jn pi by 2 by 2j. This will become sine of n pi by 2. So now our cn, the magnitude of cn, that will be sine of n pi by 2 divided by n pi, and magnitude of cn, that is equal to 0 when n is even, because that will be 0 and pi, and when n is 0 it will be 0. If n is 2 it will be 2 pi by 2, that is pi, so it will be 0. It will be 1 by n pi when n is odd. So, and c naught is equal to half of 0 to 1 dt, that is equal to half. So we have to find like power up to second harmonic. So that is equal to mod of c naught squared plus c1 squared plus c2 squared plus c of minus 1 square plus c of minus 2 square. So here c naught square will be half square, and when n is odd it is 1 by n pi. So it will be 1 by pi square, and for n is equal to minus 1 it will be minus 1 by pi square, and plus for n is even it will be 0 plus 0. So when we do it will become 1 by 4 plus 2 by pi square. So this will be the power. So the unit will be watt. So this is the power of the given signal up to second harmonic. So today we can bind up here only. And if you have any doubt, then you can ask in the YouTube comment box also. There I can reply, because most of the students would not see this lecture in live. So today we'll close the lecture here, and this video will be uploaded, and even the PDF of today's lecture will be uploaded on the Google Drive. Thank you so much for attending.